All right, so let's start. So we'll talk about Metropolis strings algorithm, and we will introduce that algorithm through this example. So consider a logistic regression model for predicting diabetes among women as a function of 4 predictor variables, x1, x2, x3, x4, and the data is given here. So let us look at the data. Peter Hoff is the author of the book that we are using in this course. So Peter Hoff, Duke Statistics, and then book. So data code to replicate figures, data code for inline examples, data for exercises. So click there and you'll find the data. I'm sure you are familiar with this web page. Okay, now first, center and scale each of the x variables by subtracting the sample average and dividing by the sample standard deviation for each variable. We do it for numerical stability. And if x is a numeric variable, you do it. But if x is a categorical variable, don't do it. So be careful about about how it is recorded, the variable. So make sure you understand, don't apply it blindly to any data set. Understand the variables, nature of the variables, and then apply. If you have a binary variable, binary or specifically Bernoulli, binary means 2 possible values, right? Bernoulli means it has 2 possible values and the values are 0 and 1, keep in mind. So that is the distinction between a binary and Bernoulli. Although we use these 2 terms interchangeably, but Bernoulli means 0 and 1. Binary means any 2 categories. So if it is a Bernoulli variable in your data, then just use it as it is recorded. No need to scale. If it is a binary variable with two categories, convert it to a Bernoulli variable, then use this. And if you have a categorical variable with several categories, it could be numeric categories or like the categories could be denoted by 1, 2, 3, 4, or categories are denoted by A, B, C, D. You convert them to corresponding dummy variables. Okay. So for example, let's say grade is a variable, right? Grade is recorded as A, B, C, D. Now it is a grade is a ordinal variable. For ordinal variable, you convert the grade into a numeric scale. You can do that. So you can call A as 1, B as 0.5, C as whatever. So it is some decreasing order or increasing order, whichever you want. But suppose you have a variable of marital status of people that is recorded as married, unmarried, widowed, okay, like that. So it has several categories. There is no underlying ordering. You cannot say the married people are superior than the non-married people and widowed are superior than married people. We cannot do that. I'm just giving you funny examples, okay? But there is no ordering. If there is no ordering, that is called a nominal variable. How do you put that nominal variable in a regression model? As a regressor, you create corresponding dummy variables. So if the variable has 3 categories, widow, married, unmarried, then you create 2 dummy variables. Okay, 2 dummy variables. Each of them are of Bernoulli nature. And if it is a continuous variable, you use them in your data. You do not need to make transformation. Any dummy variable issue is not there, but you scale them for numerical stability. So the logistic regression, when is it used? It is used if your outcome variable is of binary nature, binary or Bernoulli nature. Logistic regression is used for modeling the success probability or the probability of one of the categories. So here y equal to 1 means someone, so y1 represents someone has diabetes, y equal to 0 represents someone does not have diabetes. We wanted to model the probability that someone has diabetes in terms of these predictor variables x1, x2, x3, x4. And this is the logistic regression. When you write the probability, success probability as e to the power, the linear predictor part, this is called the linear predictor, theta, which is written as x transpose beta. And in the denominator, we have 1 plus e to the power theta. Now note that e to the power theta can take any value from minus infinity to plus infinity. Of course, they will not be exactly infinity, but any number on the real line, theta. For any value of theta, e to the power theta over 1 plus e to the power theta is always a fraction, lies between 0 and 1. That is why it's a perfect representation of a probability. This is not the only way to model the success probability. You can use the probit model. You can use other things like complementary log-log function as well. And any CDF function, cumulative distribution function, can be used for modeling the probability. So here theta is x transpose beta, and x has these components. One, the intercept term, then x2, x3, x4, x5, 5 components. So in the linear model, you have seen we wrote y equal to x transpose beta plus noise. It's very similar to the linear model, right? In the linear model, you have an error term or the noise term. We don't write that noise term explicitly, it is there. So noise term brings in the variability, sampling variability in the data. The sampling variability in the data is still here, but it is not written explicitly. So x transpose beta is a shorthand notation for this expression beta sub 0, x1 beta 1, x2 beta 2, x3 beta 3, x4 beta 4, x5 beta 5. Obviously, this parameter vector beta containing beta 0 up to beta 5 is the regression parameter vector, and it can be used to assess the effect of the predictor on the success probability. When I write probability y equal to 1, this is also referred to as the success probability of the variable. So y takes two values, 1 and 0. So y outcome is a Bernoulli variable here. Now we can interpret each regression parameter as the, now why do we take a logistic regression, not some other model? You may take other models, but logistic regression is a very popular one because these regression parameters, betas, have log odds ratio interpretation given the other variables. For instance, if I write e to the power beta 5, it is interpreted as the odds ratio of diabetes for 1 year increase of age. We can also say that the odds of the disease increases by this percentage for 1 year increase in age for the age range considered in the data. Now, a quick recap of So probability of y equal to 1 given x is e to the power x transpose beta divided by e to the power x transpose beta. The odds of the success. Odds of the success is, sometimes people write odds of the success or simply say odds, or write odds of the success probability. All are the same. So odds is probability y equal to 1 given x divided by 1 minus probability y equal to 1 given x. So for a Bernoulli random variable, the denominator is probability y equal to 0. So success probability divided by the probability of failure. That ratio is the odds of the success. Now, think of that. Suppose x has two predictor variables. Okay, so and the design matrix x is like this: x1, x2. Now, why I take two predictors? Because otherwise I have to write many terms. For simplicity, just take two predictors. Then suppose you change so let's calculate odds of the success. So when x equal to 1, x1, x2 is, if you have the logistic regression here, what happens? It is x transpose beta over 1 plus e to the power x transpose beta. And the denominator is 1 over 1 plus e to the power x transpose beta. You see there is a cancellation here. So it is e to the power x transpose beta. So the odds here, it is e to the power x transpose beta, which is beta 0 plus beta 1 x1 plus beta 2 x2. Now let's calculate odds when x equal to 1, x1 and x2 plus 1. So what I did, I'm going to calculate odds of the success at x equal to 1, x1 and x2 plus 1. So I'm just changing x2 variable, keeping x1 unchanged. Just 1 unit change in the second predictor variable. And calculate. Now I calculate the odds ratio. From x2 equal to x2 plus 1 to x2 while x1 remains unchanged is odds ratio. So you write odds one odds in the numerator, another odds in the denominator. And it is e to the power beta 2. So beta 2 is the odds ratio for changing the second predictor for 1 unit, right? while you keep the other variable unchanged. That is the interpretation. For every parameter, you will have the same interpretation. Okay, now let us feed the model to the data. So this is our model. We assume this model, and we want to feed the model to the data and estimate the model parameters such as beta 0, beta 1, beta 5, all those parameters. So that means we estimate the regression parameter vector beta. We aim to conduct a Bayesian analysis. So assume a prior distribution for each parameter. Beta 0, I assume it follows a normal distribution. Beta j follows normal distribution. And I allow them to vary. These parameters, m sub 0, tau sub 0 square, or mj and tau sub j square, these are called the hyperparameters. These are the parameters of the prior distribution, hyperparameters. So hyperparameters can be known, or if you don't want to specify the hyperparameters, you can put a prior distribution on them as well. So in this case, I assume they are known, but there is no restriction. You can put another level of prior on the hyperparameters. So the joint posterior distribution of beta based on n IID observations. In IID observations means you have observed yi and xi for n individuals. In your data set, you had n subjects. For every subject, you recorded y value, whether someone has diabetes or not, and the predictor variables. So that is your data set. Based on that data, you have the posterior distribution of the parameter. And the first part is the likelihood part, and the second part identified as the prior distribution. Prior distribution for all parameters, beta 0, beta 1, up to beta 5. Now, why the first part? Look at the first part. It is the likelihood of the data. Likelihood for Bernoulli observations. So you have y1, y2, yn, Bernoulli observations, right? So the likelihood of the parameter given the data means y1, y2, yn, as well as x1, x2, xn. Now here, when I say x1, x2, xn, these are x1, x2, xn. Each of them are vector. Okay, each of them are vector containing 5 predictor variables values. So to be specific, you can put a tilde sign at the bottom to denote that they are vectors. So first you write the probability, success probability e to the power x transpose beta divided by 1 plus e to the power x transpose beta. If yi, now write I here, if yi is 1, then you write the success probability. If yi is equal to 0, observed yi for a subject is 0, that means you write the failure probability. So I write the success probability raised to the power yi, and failure probability, which is 1 over e to the power xi transpose beta to the power 1 minus yi. Now look at it carefully. When yi equal to 1, that means you observed success, then this term will be there, and this term becomes 0. Anything to the power 0 means 1. It will not contribute anything. And when yi equal to 0, then yi equal to 0, that means this term will disappear and only this term will exist. That is what we want. Therefore, this is your likelihood. And we have n IID observations. Therefore, you take the product over I is equal to 1 to n. Now, I can put this yi right here and yi right here, right? And this one. Next. E to the power xi transpose beta yi. And look at this. This part and this part together, yi and 1 minus yi. When you take the product, you add the powers. If you add the powers, it becomes 1. Therefore, the denominator is 1 plus e to the power xi transpose beta. No yi is involved in the denominator. And you have, you have this expression. That is the reason. Okay, the posterior distribution. So this is the posterior distribution. Is not in any standard form, in any standard distribution. Not normal, not gamma, not exponential. You may see that this part, prior part is the normal. But when you multiply this with this likelihood, the distribution of beta, any component of beta is not normal. It's something. So to figure out the characteristics such as posterior mean, median, or any characteristics of the posterior distribution, we need to draw samples from this complex posterior distribution. And one way of doing so is via the Gibbs sampling. How do you sample all components of beta from the posterior distribution, joint posterior distribution? You draw beta sub 0 given the rest of the parameters from its full conditional distribution. Now, full conditional distribution of beta 0 involves the likelihood and the prior part of beta sub 0. Notice that the likelihood, you cannot separate out the contribution of beta sub 0 and the rest of the parameter in the likelihood. They appear in such a complex way that you cannot separate them. Similarly, conditional distribution of beta 1 involves the likelihood in its full form times the prior distribution, so on and so forth. The full conditional distributions are also not a good looking distributions, not a handsome looking distribution, beautiful distributions. So they do not match with the form of any known distributions. So how will we sample from these non-standard distributions? We will use the Metropolis Hastings algorithm. So the idea is the following, that suppose that we want to sample from a density F, and the variable is X. Okay. This X has nothing to do with this predictor variable. So this X is a generic variable, and this is the density function. This density function has a complex form so that I don't know how to sample from it easily. This density is called the target density. So let X superscript K be the sampled value at the kth iteration for K equal to 1, 2, 3, 4. And for the next iteration, K plus 1th iteration, we sample from F as follows. So we generate a new value X star from a distribution Q given Xk, then compute the acceptance ratio. What is that? This is defined as follows. This is the ratio of the target density evaluated at the newly proposed value to its old value multiplied by the ratio of Q evaluated at Xk to X star. So this is the acceptance probability calculated. Then you sample a random number from a uniform distribution between 0 and 1 and check if this random guy U is smaller than this acceptance probability. If it is so, then you set Xk plus 1 to be X star. Otherwise, you set Xk plus 1 to be Xk, its original value. So notice at the last step, K plus 1th iteration value would be the previous iteration value, Xk. It can be Xk or it can be the newly proposed value. So this X star is sampled from Q. This Q is called the proposal distribution. And we need to make sure that sampling from the proposal is very easy, right? Why are we developing this algorithm or learning this algorithm? Because sampling from F is not easy. So to mitigate that problem, we take help from another distribution called proposal distribution. Number one criteria of the proposal is that sampling from this distribution must be very easy. And this proposal distribution is the kingmaker of this algorithm. Kingmaker means controls everything, right? Even more powerful than a king, right? Kingmaker, who makes the king. So the distribution, this algorithm's efficiency depends on the choice of this proposal distribution. Now there are different choices. The proposal is called symmetric if the conditional distribution, conditional density of Xk given X star is same as conditional density of X star given Xk. If that happens, that is called a symmetric proposal. Why do you pay attention to a symmetric proposal? Because if it is symmetric, then the calculation of acceptance ratio is very easy. If it is symmetric, then there is a cancellation of these two terms. And acceptance ratio is simply the ratio of the two target densities. For example, if Q proposal distribution is a normal density with center at X star and standard deviation omega, then the density function is symmetric, right? Normal density function is symmetric. Another example is the uniform distribution with mean X star and support like this. Now you may wonder that this is the algorithm where sampling is done from Q, not directly F, but we are still using F in the acceptance ratio calculation, right? Yes, we are still using F in the acceptance ratio calculation, but we are not using F directly to sample from. Calculation of the density, evaluation of the density at a point, and sampling from that density, these two are different things. Evaluation can be done relatively easily, but sampling may not be easy. Another very important point is that this target density appears only at the acceptance probability calculation, and it appears as a ratio. Therefore, if you do not know the normalizing constant or the constant of the proportionality of your target distribution, you are perfectly fine, because this constant of proportionality will appear in the numerator and denominator, and they will be cancelled. So what you need, just the functional form. And that is a great advantage. It's a very great advantage of the Bayesian computation. Going back to this, to either the joint distribution of beta or the full conditional distribution of beta, in any case, we do not know the constant of proportionality for this distribution. And calculation of this constant is very difficult, because it requires integration with respect to multiple parameters. So it is a multidimensional integration. But we are lucky, we do not need to pay attention to the constant of integration or the proportionality constant, because it cancels from the acceptance probability calculation. So clearly, if the proposal is symmetric, then the ratio of the proposal densities in R cancel, and this special case is called the metropolis algorithm. And the acceptance ratio becomes this. So originally, metropolis idea was take symmetric proposal, normal proposal, and then you calculate the acceptance ratio. Later on, it was extended with the other researcher that suppose you don't have the normal proposal, you take some other proposal distribution. How are you going to modify the acceptance probability? And then this general form of the acceptance probability came in, evolved. So you do not need symmetric proposal distribution. You can start with asymmetric proposal distribution, but in that case, you modify your R calculation. Another thing is, this is a Markov chain Monte Carlo algorithm. This is the overall structure is the Markov chain. That means it is a chain. One iteration depends on the other previous iteration, right? And here it is explicitly when I say generate X star from Q. Q is a proposal distribution that depends on X sub K. Look at this, X sub K, X superscript K is the kth iterative value. So it depends on the kth iterative value. It allowed to depend. If you don't want it to depend on X sub X superscript K, it is fine, and it is called independence sampler. And in that case, you just take the ratio of the corresponding density function, target densities, and the proposal densities. Now, if Q is a good match to F, then using the independent sampler will be close to generating independent observations directly from F, which is a good news. We want independent observations, right? Because independent observations will give more information than dependent observations. If you generate 10,000 observations and they are dependent, you have seen the effective sample size. The effective sample size will be much smaller than 10,000. Therefore, independent observations are always preferred. And if Q is a good match, if your proposal density closely resemble with the target density, that is the best thing. But if Q is not a good match to F, then independent sampler can perform very poorly. And that is a very important message, that for the sake of easy calculation, we prefer to take independent sampler, right? But your convergence will suffer. And it's very hard to guarantee that your proposal distribution is close to the underlying target density. It's very difficult to guarantee. If it is a univariate or if it is a scalar variable, maybe you can check it. But for a multivariate scenario, like most of the problems, it is not easy to check whether Q is close to F. So now if X has M components, is a vector of length M with joint distribution Px, the joint distribution can be known up to a constant of proportionality. What is the meaning of that? It means you do not need to know exact density function. As long as you know Px is proportional to some function of X, you are fine. And this is the algorithm for k equal to 1 to ... What it means that k represents the number of iterations, how many times you want to repeat this procedure. For j is equal to 1 to m, m is the number of components of the vector. Generate xj star from qj. This is a proposal distribution for that jth component. Compute the acceptance ratio, and then you set the jth component at the k plus 1th iteration to be like this expression, depending on whether this random draw u is smaller than this acceptance probability or not. And then you do it for every j is equal to 1 to m. So you have to repeat it for every component separately. And then you repeat this entire thing as many times as you want. These are acceptance ratio. Is a ratio of positive quantities, right? So this P here, Q, density functions, they are positive, okay? And so this ratio could be larger than 1. If it is larger than 1, you just set it to be 1. Questions? So this is the algorithm. Now, some comments about Gibbs, Metropolis strings, and MCMC. So if Qj, this is the proposal distribution for the jth component, is same as the conditional distribution of xj, jth component, directly derived from the joint distribution, or this is the full conditional distribution of xj. So then we get Gibbs sampling, right? In Gibbs sampling, you calculate the full conditional distribution, and if you sample directly from the full conditional distribution, that is our original form of the Gibbs sampling. Thus, we can create an MCMC algorithm for the target distribution P, in which each element of xj of x is in turn sampled from the full conditional distribution. Use a Gibbs step if direct sampling from the full conditional distribution is feasible, or use a metropolis testing step if the full conditional distribution is only known up to a normalizing constant and is not feasible to sample. That I forgot to write it. Often this is done using the proposal distribution that does not depend on the other components. Yes.
Earlier, the sampler says it performed very poorly. Does that mean it won't converge, or just converge very slowly?
Which one?
Oh, you're looking at independent samplers.
Oh, independent sampling. Okay. Yes. So it will perform poorly. That means it may not even properly converge to the target density. Now the thing is, theoretically, there should not be any problem, theoretically, but within a finite number of iterations, it may not go to the target distribution. In theory, there should not be any issue. But it may wander around quite far from the truth. All right, so now I'm going to code this logistic regression using this metropolis strings algorithm. So n, which is the length, number of observations in the data. P is the number of columns of this X matrix. Beta initialized parameter, we can set all of them to be 0, initialize all the parameter, because this is a chain you'll be running, right? So you need to initialize some value. You can set some other value like 0.1 or something, but my suggestion is don't set something very absurd, because you never know. You do not know for a finite number of iterations what would be the influence of the initial value. If the initial value is too far from the truth, it will take a long time to converge to the truth. So don't take something like 1,000, 5,000, those random numbers, big random numbers. Don't do that. So here it will be sample values will be stored, prior variance for the normal prior on beta. I put prior variance 100, standard deviation 10. Log likelihood. So this is important. Acceptance probability calculation. This acceptance probability. We don't calculate the ratio as such. We calculate the log of that ratio. The reason is, if you try to calculate the ratio often, this ratio will be very small, like 0 over 0, that type of thing. So to avoid that numerical issue, calculate log. So log of the likelihood, log of the likelihood is, remember, this linear predictor part, right? So you have when you take log, then it becomes this guy, right? Minus log of this guy, right? So this guy, y times x transpose beta minus log 1 plus e to the power x transpose beta. And sum, this summation is over all observations in observations. And we are also calculating a log prior distribution. Why do we need it? Because our full conditional distributions involve the prior distributions as well. So keep in mind, when we calculate, when we write our Metropolis Hastings algorithm, then our target density is this guy. Target density is the full conditional distribution. Okay, because I'm not able to sample from this full conditional distribution. I'm taking help of Metropolis Hastings algorithm. So beta prior, now we put all the betas together, okay? And then this is the MCMC sampling loop. This outside loop is over the number of iterations, and this inside loop is for every component, beta component. So here what I'm doing is sampling beta star j. So jth component of beta vector sampled from a proposal distribution. What proposal? I took a normal proposal distribution with mean beta sub j. So previous iteration value as the mean value and standard deviation of 0.1. This is the proposal standard deviation. And then calculate the acceptance ratio for this component. So log likelihood of the current, log likelihood of the start, that means at the proposal value, and log of the prior current, log of prior start. Beautiful thing is the ratio of the proposal, you do not need to calculate because the proposal is symmetric. So that cancel. And the log of acceptance ratio is then star plus this prior minus this quantity. And if you see, I calculated log of acceptance ratio, and I'm supposed to check if a uniform random number is smaller than R. So same thing, I do log of that uniform random number is smaller than log of R. So checking this, if it is so, then my new value of beta is beta star. Okay. Beta star. Now I'm checking whether I did anything wrong here. Okay, so can you run this one at home, get the results, and make sure that I did not do anything wrong? Why? Why am I worried? I'm worried because check it whether I did anything wrong. Beta star equal to beta, I write here. Look, this and here this beta equal to beta star. I believe I did not do anything wrong because, yeah, I did not do anything wrong because this beta star is a vector and I'm just updating the jth component. So it is fine. I was concerned whether I mixed up a vector with a scalar because here beta appears here also. It's a vector. Beta is a vector of regression parameters. So just copy, paste, and see the results, convergence diagnostics, simulated data examples. Next day, we'll talk about checking the convergence of a chain.